Okay, so let's get going. You should see this whiteboard. Okay, so again, there's just again, the announcement is no quiz. I still don't feel like we've quite covered enough. Plus, I want a little bit of a gap so that when I ask the quiz questions, it's about stuff that you sort of absorbed a little more. So definitely next week we'll have some quizzes, maybe even two. Yeah. So where were we last time? Last time we were looking at bonding, and what we were talking about is if you have two or more atomic centers, say carbons, and we were trying to understand what happens to electrons that feel the Coulomb interactions of these atomic centers. What kind of energy do these electrons have? And we argued that if we had, say, two carbons, well, there's going to be some Coulomb, attraction between the electron in each atom, and that'll have it'll generate some kind of bound state, right, with some energy. And so for the electron, we argued that if there's two of these guys, then, well, the electron can either sit in this place or this place, these two bound states, and they'll have some associated binding energy. But there will also be some transitions, right? The electron, if it's sitting over here, there'll be some transition probability of it hopping from 1 to 2 and vice versa. And those kinds of transitions are captured by off-diagonal terms in the energy. And we saw that for this kind of ethylene molecule, which has a bunch of the electrons paired off in sigma bonds. And so we don't worry about those because those are kind of taken care of. And then there were two leftover electrons that we needed to figure out what happens to them. And so we argued, well, that each of those electrons will have this kind of Hamiltonian. And if we diagonalize this Hamiltonian, there's two eigenvalues. And the two eigenvalues are, lambda plus or minus, just E naught plus or minus A. And the associated eigenstates, phi plus or minus, are just the two combinations of the two bound states. It's the two combinations, either the symmetric combination of the two bound states of the two carbons or an anti-symmetric one. And for most kinds of bonds, the electrons want to be in the symmetric combination. So that's why A is defined the way it is. For positive A, right, for plus A and minus A, if A is a positive number, the lower state is E naught minus A, that's the ground state, it's the lower energy, and that corresponds to a symmetric combination of the two bound states, right? You got, if you were to write it out as a wave function, right, we could write it as x, phi minus, that would be the ground state. It would be 1 over square root of 2, right? It would be the ground state associated with, it'll be the wave function associated with carbon 1 plus the one associated with carbon 2, right? It's, well, where this guy, right? This guy is x dotted into the 0, 1 state. So I guess I would call that phi 2. Phi 2, it's 0, 1, that the bound state on the second one, the second carbon. Then this is X dotted into phi 1, where, you know, phi 1 is the other basis vector, that guy. So it's just a symmetric combination. So that's the model, and we're generalizing it now to an arbitrary ring. And so the energy here of this ethylene guy, there's 2 electrons that we need to put, so both of them can sit in that ground state, the phi minus ground state. So we're doing the same thing, but looking at it more generally, and we argued that for a ring of carbons, where you get carbon 0, carbon 1, carbon 2, and so on, that if phi n is the basis here of bound states, right, where each phi n, you know, from 0 to n minus 1, that describes the electron sitting at a particular carbon. If that's your basis, then how does the Hamiltonian act on one of these basis vectors? Well, it's easy. There's the diagonal piece, which just gives us the bound state energy. And then there's the hopping terms, again, that describe transitions between the carbon that you're sitting at and then the 2 adjacent ones to the left and right. And it's all periodic, so you have periodic boundary conditions. So how do you solve this kind of thing? Well, what you do is you introduce a hopping operator. You can introduce a U, and it's going to be U for reasons that we'll see. It's going to be pretty obvious that it's going to be unitary. But the unitary, what does it do? It takes one of these basis states and just hops to the next one. It makes a transition from one basis for the bound state at carbon n to the one at the n minus 1 carbon. And then, of course, it's unitary because we can make it a unitary. And in particular, then, if we take the U dagger on both sides, right, then we see that this is just going to be the identity. And see that U dagger then must take us in the other direction. If we take U dagger and act with it on this guy, then it'll just increment the vector. And we can just define this operator. And then our Hamiltonian, we can write it in terms of this operator as just, you know, there's the diagonal piece, and then there's a minus A, and then a U plus a U dagger. So, yeah, and obviously H will commute with U dagger. So, so in order to find the eigenvalues and eigenvectors of H, it's convenient to think about the eigenvalues and eigenvectors of U first. So if we can find those, then since H and U, they commute, we can find sort of a simultaneous set of eigenvectors. And of course, the eigenvalues will kind of easily follow from this, right? And you see that the unitary, it comes in is this U plus U dagger thing that's important. That ensures that H is Hermitian, right? If we take the dagger of it, then this just becomes dagger and this becomes dagger. And so, you know, you get back the same thing. H has to be equal to H dagger. So it's still, everything sort of works as it should. You have this unitary, H is a Hermitian, and the operator is defined, how it acts on the basis, and we define it this way, and we'll just see what happens. So what's the idea? The idea is, imagine you hop all the way around the ring, right? You take the U and you keep going. So in this case, it goes to the left, right? You subtract 1 from n each time you apply the U. So U takes us this way, and U dagger takes us the other way. Imagine hopping around the whole ring, right? You just take U and you hop, 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 and you go back to where you started. Well, if you go back to where you started, you must get back out the same state, right? So what does it mean? It means that we have a constraint, right? U raised to the nth power, where this is the number of carbons or number of atoms in the ring. That has to be equal to the identity. And moreover, the eigenvalues of U, since it is a unitary, remember that the eigenvalues of a unitary matrix, they always have the form e to the I delta, where delta is just some phase, right? Unitaries have to have that just from, since U dagger U is equal to I to the identity. So if you just recall from the first semester, that's eigenvalues of unitaries always have that form. So what does it mean? It means that the eigenvalues satisfy the following, right? That if you take the eigenvalue and raise it to the nth power, right, it has to give back 1 just because of this constraint. So, and that means that the possible eigenvalues, the only options there are that they're multiples of 2 pi over n, right? Because that's the only way this delta will give us 1, right? This delta has to be a multiple of 2 pi. And so these deltas, the only possibilities are, of course, it can be 0. E to the 0 is 1, but it can also be a multiple of 2 pi over n. And the unique ones are 1, 2, all the way up to n minus 1. So these are the eigenvalues, and you see there will be n of them, right? Starting with 0, and then the largest one is 2 pi n minus 1 over n. And so that's great. So we can, we now know the eigenvalues of the U operators, and we can, by extension, write down what the eigenvalues of the Hamiltonian are. But let's think a little bit about the eigenvectors, right? So we have the eigenvalues. Let's think about the eigenvectors. So what's the eigenvectors? So let's, we can of course do the usual thing and expand our eigenvectors into basis. And our basis is just those bound states. So we can write an expansion, right? Cn, phi n, always allowed to do that. And of course, they're going to be normalized. So we're going to choose the coefficients such that our eigenvectors are normalized to 1. So let's just see what happens when you act with the U operator here, right? U acting on one of these guys, which we are supposing is an eigenvector. Well, what will happen is you'll have a sum, right, from 0, n minus 1, Cn. What happens here is that this becomes phi n minus 1, right? Because the U hops us over by 1 state. So this goes from phi n to phi n minus 1. And so we can re-index, because we have periodic boundary conditions, we can change the sum so that we can add and subtract any number we want to this n, right? Because we're always summing around the ring. So as long as you sum over all the elements of the ring, it doesn't matter where you start in that summation. So we could just as easily start at n plus 1 instead. So we can just add n here. and get this. It's the same thing because we're still summing over the entire ring. And we have the full kind of periodic ring there. So it doesn't matter where we start. There's a sort of, it's a sort of discrete rotational symmetry, right? We can rotate however many times we want, start the summation however we want. And so this is supposed to be equal to, right? If it's an eigenvector, it's supposed to be equal to the eigenvalue, the associated eigenvalue, which, you know, this is for some S, right? Where these are the eigenvalues. So it's going to be that eigenvalue, Cn phi n. So that gives us the solution to the eigenvectors, right? Because we see this has to be equal to that. We get another recursion relation. So you see recursion relations come up all the time in solving quantum mechanics problems. We saw that for the hydrogen and so on. But here it is for this toy model of bonding. You see, you get this recursion relation of those things have to be equal. So all we have to do now is, so as long as we know what the first coefficient C0 is, then we can figure out everything else, right? And C0 we can get simply by looking at this, right? C0, the first coefficient. Well, the way we can think about it, right, is if we can just look at the case where the eigenvalue is 0, right? And then all the coefficients are the same, because this just becomes either 0, it just becomes 1. So C0, the only option for it, in order for this normalization condition to hold, is that it's 1 over square root of n. That's the only thing that will give us the proper normalization, right? Just from the case where you can set delta equal to 0, then all the coefficients are the same, and then, you know, this just becomes, this condition amounts to saying that n, which is a number of terms in the sum, right, C0 squared, since they're all the same now, is equal to 1. So you have to have this. So, okay, that gives us the whole thing, right? That chi of S is equal to 1 over square root of n, sum over little n equal to 0 and minus 1 of E. And then, you know, the other ones are just, each time you go to the next coefficient, you multiply by this factor. So you multiply by a total of n times, right? Delta S. And that's written in terms of this phi n basis. So these are the eigenstates. Okay, right? Does that make sense so far?
Yes.
Okay, good, good. So let's go back now to the Hamiltonian, right? And ask what are its eigenvalues. So back to the Hamiltonian. And for the Hamiltonian, well, again, it's easy because, well, the identity part will just give us the E0 that's already diagonal. So that's, you know, that doesn't change. And the only other part is now you replace U with its eigenvalues. And the eigenvalues are, again, it's just this guy plus e to the eigenvalues of U dagger. Of course, if you dagger, the eigenvalue just gets complex conjugated. So you just get that. And what's this guy in terms of a more familiar function?
Is that cosine?
Yeah, yeah. Nice. It's just the cosine. Well, it's twice. 2a cosine delta S. And we can put back the eigenvalues, and what we get is 2a cosine 2 pi s over n. So you see now it's a little more complicated. Before, when we just had 2 carbons hanging out, right, our eigenvalues were a little simpler. They were just plus or minus a. Right now it's a little bit more complicated. We get E0 minus 2a times this cosine. So you can actually get a smaller. So it's a little bit more complicated, right? When this is 1, right? When the cosine, say s is equal to 0 here, that would mean the cosine is equal to 1. The ground state is actually E0 minus 2a, right? It's not E0 minus a as we would expect for just 2 carbon centers. When the electron has the ability to hop around this ring like this, the ground state is actually smaller than just minus a due to the hopping. It's E minus 2a. So let's do an example. So let's do the benzene example, for which n is equal to 6. That's 6 carbon atoms. And again, these are the single bonds. And of course, you got the H's hanging out. And again, so each carbon now will contribute a little electron that has to hop around this ring. So there's 6 electrons that we have to place. Okay, so let's do it one at a time, right? So first we can place 2 electrons, go to the ground state, which is the s is equal to 0 state. So that energy would be 2 E naught minus 2a, right? 2 electrons go there. Then we can look at the next state, so the next state where this cosine is as close as you can get to 1 is the one where s is equal to 1. But notice there's a symmetry here. This cosine, it's because it's periodic. If we take 2 pi s over n, that's the same as cosine of 2 pi n minus s over n, right? Because it's just a periodic thing. So the s equals 1 state is the same has the same energy as the n minus 1 state. So those are actually the same. They're doubly degenerate. So that energy level corresponding to s equals 1 is, or n minus 1, those two things, that it's it's degenerate, right? So actually 4 electrons can go into that state. And what's that guy? Well, the energy there is E naught minus 2a, and it's cosine of 2 pi over 6. And that's just a half. So this is just E naught minus a. That's the same as the what we found for the 2 carbon case. So four of the electrons can go there. So that energy is 4 E naught minus a. So it's this guy and this guy, right? And so overall, what's the ground state of benzene? The ground state of benzene in this model is, so you get 2 electrons in that ground state, and you get 4 electrons in this next excited state. And that gives us a total of 6 E naught minus 8a. So you see it's a little bit lower than we'd expect from a 2 carbon situation that we looked at last time, right? This guy. So the 2 carbon situation, again, is describing what a double bond energy is, just between the 2 carbons like this. But you see in benzene or in a ring, because of the ability of the electron to like delocalize around all of these carbon centers, you actually get a little bit more energy benefit from that. In the case of benzene by an amount 2A, more than what you'd expect if you were to just naively assume that the benzene molecule just forms a bunch of double bonds, right? Here, if we were just to count the double bonds and assume that each one of these contributes the same kind of energy as the little ethylene we considered, right? We would have 3 of them, and each one would contribute an energy of 2 E naught minus A, right? So that would give us 6 E naught minus 6A. And that's not right, right? The real ground state is a little bit lower than that because of the stability of the thing to delocalize. And what's interesting is that you can actually figure out what A is, right? So this is what I was talking about in recitation a little bit, and also last time. The question is, how does A related to anything, right? This is like a toy model, right? And how is it related to like the Coulomb potential and the actual details of the interactions of the electrons? And that's complicated, but it doesn't matter because you see we're able to get what the ground state is. And if we do that, we can now use an experiment to actually measure A directly. So what you can do, for instance, is figure out A from enthalpies of reaction. You can figure it out from basically calorimetry. So you can take a reaction, say you take C6H6, which is the benzene that we talked about it, and we can have it undergo a reaction where we break up all of those. We break up its bonds by adding 6 more hydrogens to give us C6H12. And what's C6H12? That's 6 carbons, and now each carbon has 2 hydrogens attached. So all of the electrons are paired off in the sigma bonds. So it completely breaks up the double bonds between the carbons. So it eats up all those electrons that we placed using this toy model. It eats them up by binding them to hydrogens. So when it does that, there's some associated energy with that reaction, and that's 49.8 kilocalories per mole of reactant. So that's good. And so what would you do now? You would compare that to breaking a single double bond and seeing what happens there. So imagine we can look at C6H10, and we could break that with 2 hydrogens. So what's C6H10? C6H10 is where, again, you got the 6 carbons, right? And H10 is where everything is paired off except for 2 carbons, which will have a little, so it's like having a little mini ethylene here in the middle of the carbon ring, and everything else is paired off. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. And so there's 2 leftover electrons which get paired off in the double bond. So this is like a little ethylene guy. And this guy, if we hydrolyze it, right, and form C6H12, that also has an energy associated with it, and that's 28.6 kilocalories per mole. And so what it means is that, and this would be the energy associated with the single double bond. So we can actually get what 2A is, right? What is 2A? Well, 2A must be the difference, right, between 3 of these double bonds, which would be this guy. So it's 3 times 28.6 minus the energy associated with breaking up the benzene ring. All of them in the delocalized state. So this is 49.8 kilocalories per mole. And that, you work it out, is 36 kilocalories per mole. And then you can do the unit conversion for per mole is, per Avogadro's number of molecules. You can do it for a single guy. You convert these units to just electron volts, and that's 1.6 electron volts. So it's pretty sizable. Remember, like room temperature, in the first semester, I told you that room temperature is about like 1/40th of an electron volt. So this is a sizable energy, this hopping energy. And why do you get this gain of 2A in the benzene? Because it doesn't just form a bunch of double bonds like this where the electrons are just localized between these 2 carbons here. What it does is, because of the hopping, the electron actually is able to delocalize around all of the carbon centers. And so the benzene is more sort of stable because the electrons actually delocalize. And we can see that in the simple toy model, right? You can actually calculate what the eigen states are of say the ground state. You'll see that it's just a symmetric combination of all the 6, right? We know what it is, right? If we look at here, what's the delta equals 0 state, right? It's a symmetric combination of all the bound states at each carbon center. It's completely delocalized around the whole ring. So that's why when you see chemistry books and papers and stuff, and you see a benzene ring, they don't put just a bunch of double bonds like this, unless there's extra hydrogens or something that pair off the electrons. A benzene ring looks like this. It's always drawn like this schematically, right? The little ring in the center. And this ring corresponds to the idea that in the ground state, the electrons are actually delocalized around all the carbon centers. All right, so that's rings, molecular rings. And on the homework, you'll do a linear chain. Now, a linear chain is kind of similar, except you have to start worrying what happens at the ends, right? If you have a chain of carbons, right? And you start having to place, you think about what the electron senses. Sure, it can hop left and right here, right? But once it's at this location, your Hamiltonian has a slightly different structure. It loses that periodic symmetry, and there's only one hopping term in the Hamiltonian associated with this carbon. That's the one where you just hop back there. So it's a little bit different. So you have to worry about the limits of these sums, what happens at 0 and n-1, but the problem sort of guides you through that, and hopefully it's interesting to you. So I think that's it's a good problem. Another kind of part of that homework problem, which is interesting, is that it tells you how you might calculate the order of a bond. So oftentimes, I would call these, when these 2 extra electrons pair off, right, that's a double bond. And, if you have another 2 that pair off, you can even get triple bonds. Well, you can use this simple model to calculate the bond order. And so that's part of the homework, and you'd be able to calculate that this, for instance, has bond order 2, right? That makes sense, because it's, it's the definition, it's a double bond here. But for something like benzene, where the electrons delocalize around all the carbons, you don't get exactly 2, right? If you calculate the bond order between any 2 carbons in a benzene, it's not necessarily exactly 2. You can get sort of fractional bond order. So this idea in chemistry that things are always single, double bonds, and so on is not quite right. It's not even true for like for a linear chain, and that's something else you will see on the homework. It's kind of interesting, is that if you have a chain of carbons, say 4 of them, like a double bond, here that's how you draw it in chemistry, but it's not quite right because you have to actually calculate what the ground state is. You actually have to do the eigenvalues and eigenvectors. That's what really tells you about what the structure is, right? Because it's the eigenvector that determines how the electrons are localized, whether they're really localized just symmetrically between these 2 carbon centers, or whether there's some delocalization across here, that maybe some of the electron density also exists at these end guys as well. So, and it does, so that modifies the bond order. It's, having a linear chain of 4 carbons is different from just having 2. Obviously with 2, you're going to have a symmetric combination between the 2 carbons in this model. As soon as you have 4, there might be some weight, extra weight of the in the eigenvector associated with the bound states at these edge carbons. So you'll see that, and hopefully this is starting to make sense. This for those of you, I assume most of you don't really haven't taken many chemistry classes, but if you ever do, you'll see that this very simple quantum mechanical model can actually explain a lot of the stuff that's going on there. But hopefully you get a flavor of the kinds of assumptions and things that go into chemistry. But you can actually work out a lot of them just by doing very simple finite dimensional quantum mechanics, just by looking at this kind of toy model. Any questions about bonds and so on? So again, the idea is for any molecule, so let's just again talk a little bit more abstractly. For any molecule, any chain, and I use carbon, but it's anything really, you're always wondering what does a single electron see in terms of the potential. And we always have as a basis the bound states of the electrons sitting next to each one of these carbons or atomic centers. That's always our basis. So that's always, for these 3 guys, this is our basis. Each of these states corresponds to the electron sitting at each of those carbons. And then the energy always has something to do with the energy, the bound state energy, that's sort of the energy associated with those bound states. And then there's a hopping term which has an off diagonal, which contributes an off diagonal piece that's gives you a minus A for that off diagonal component that connects the 2 different bound states together, and that's the hopping. And then any kind of crazy molecule you can think of, any kind of thing you can associate with it, any graph like this, you can associate with it a Hamiltonian, right? That's always, this is going to be a 1, 2, 3, 4, 5, 6, a 6x6 matrix, and with hopping terms associated with each of these links. And then you can find the eigenvalues and eigenvectors, and the smallest eigenvalue is going to be where the first electron goes. And that's how you can start filling up the energy levels of this molecule. However many electrons you have, that's, there's 2 electrons that can go in each state. And that's how you start filling up the energies. And that's how you can calculate the total energy of the bonds in a molecule. And then how would you calculate, and that, that tells you something about what happens when you have a reaction that sort of breaks those bonds. And binds the electrons, say, to hydrogens that you put in. So yeah, that's the, hopefully you understand the sort of general idea of what's going on. And again, you'll practice this on the homework with a linear guy. All right, anything else before I move on? Okay, so the other application, see, this is also serves as a bit of a review of the first semester. What did we do? We looked at angular momentum and radial potentials. That's for the hydrogen. We now reviewed basically discrete, sort of finite dimensional quantum mechanics, where you just have matrices and you find the eigenvalues and eigenvectors. Let's talk about, and we did, molecular energy states as an example of that, as an application, and trying to figure out some energies of bonds. And now the last thing that we kind of sort of quote unquote review is time dependence, right? That's the last bit that we that was fundamental in the first class. And the major application of that, of the time dependent Schrodinger equation, well, it's NMR, nuclear magnetic resonance. And the basic principle there is you have a spin 1/2 particle. It's typically a nuclear spin, right? That's the nuclear part. It's the N of the NMR. And what you do is you align the spin with some B field, right, along the Z direction. And we know that the energy associated with that is the magnetic moment dotted into the B field. And it's going to be along the Z direction. And so this thing is 1/2 h bar times a kind of a characteristic angular frequency, right, omega naught, times sigma Z, right? And that comes from the moment, right, that's proportional to the vector of Pauli matrices. That was a spin 1/2 business that we covered in the first semester. And of course, sigma Z is just the Pauli matrix, 1 - 1, 0, 0. And of course, that's our spin 1/2 Hilbert space, right? A two-dimensional Hilbert space. The two states are spin up and spin down. That's our basis, right? Spin up has an energy of minus h bar omega over 2, omega naught over 2, because that, if it's spin up, then it's aligned with the field in the Z direction, and that's favorable. If you spin down, that's less favorable. So that has h bar omega naught over 2 as its energy, right? So it's got a larger energy if you're anti-aligned with the field. And what's the idea of NMR is that you apply another field. You have this field that aligns the thing, but then what you do is you apply another field in a direction that's perpendicular to the aligning field, and that we're going to call delta B. And this delta B, it's actually going to rotate around in the XY plane like that. And so that's the idea. If I were to draw the coordinate system here, this is along the Z direction, and then these guys, this delta B is going to be rotating around the XY plane, just like that. It'll rotate around like this with some frequency. And you apply this oscillating field with some kind of coils, some kind of, you pass a current through some solenoid type things in one of these NMR devices. I'm not going to get into the details of the device itself. I just want to go over the basic physics of it. Actually, it's covered pretty well in the Bellac book in the last two sections of chapter 5. So in Bellac, we're kind of looking at chapter 5, and we're going to cover sections 1 and 2. And then 3 and 4 are also very interesting, and they're more applied. And you can read those if you want to know the details of actually how NMR works, like the actual like spectroscopy and so on. But I won't really cover that. It's not. The important thing is the physics of what happens when you have these two fields. So that's what we're going to do. Anyway, so you have this oscillating field, and so that's going to contribute its own energy, right? Like an H delta associated with that thing oscillating. And of course, it's the same kind of energy. It's the moment dotted into the applied field. It's the same thing. And now, in principle, because this other applied field can have a different magnitude, right? It's going to have a different associated frequency, right? Omega 1, right? That has to do with the magnitude of the field, right? It's a combination of mu and of the gyromagnetic ratio, right? And the magnitude of the field, right? If you go back and look at the notes from the first semester. And now you have, instead of it pointing along the z direction, it's in the xy and it's rotating around. So the operator associated with that is sigma x, that's the x component, and that's going to pick up some cosine omega t. And then there's a y component that's going to pick up a minus sine omega t. So it's just oscillating around the xy plane. That's what this delta B is. And that's these two terms right here. And the oscillation angular frequency here is omega. And this guy right here, so that's just the applied field frequency. You see, that's the thing that we actually apply. This guy is called the Rabi frequency. And again, that has to do with the magnitude of the applied field, basically, and the the gyromagnetic ratio of the spin. And this guy is called the Larmor frequency. And that we already know about that. That's the kind of fundamental frequency associated with precession of the spin and just the applied field in the z direction, right? If you just have a uniform field applied in the z direction, it's the frequency of the spin precession. We already looked at that problem last semester. So now you have these 3 different frequencies, and the idea is trying to solve this problem, getting its time dependence and doing all that when you have a constant field applied in the z direction and an oscillating one in x and y. So that's the idea. And you can, of course, combine both of these into your total Hamiltonian, which is, I'll call this one H0, and it's just H0 plus H delta. And you can write it in a nice way if you expand the cosine and sine in terms of complex exponentials. You recall what the Pauli matrices are. This just reduces to minus h bar over 2. Then what do we get? On the diagonals, we get omega naught minus omega naught. That's just from the sigma z. And then the other ones combine nicely to omega 1 e to the I omega t. And then, of course, it's Hermitian, so it's the complex conjugate down here. So that's the Hamiltonians, time-dependent Hamiltonian with these oscillating off-diagonal terms. And now what do we do? Well, it's easy. We just have to solve, the only equation we ever really solve, which is the Schrodinger equation. But now, of course, your Hamiltonian is time dependent. So what do? It's the usual thing. We expand in a basis. The basis is just, the spin up down basis. So we say, fine, our states are going to be some combinations of up and down. And these are, some time dependent coefficients. And we just rewrite the Schrodinger equation in terms of this basis, right? We know what H is. So we just plug this into the Schrodinger equation and write down the set of equations for C up arrow and C down arrow. And of course, it's all normalized, so there's the normalization condition. There's, of course, this constraint. Okay, so what do we get? We get that I, and then the derivative of C up, down, dt is equal to minus plus 1/2 omega naught C up, down. That's the diagonal pieces, right? The H bars cancel on both sides. You just get the 1/2 minus omega naught for the up arrow. That's just this diagonal piece, minus omega naught for the down case. That's just the diagonals. And then you have the couplings between up and down. And that's generated by the off diagonal guys. And that's 1/2. And now it's omega 1 e to the plus or minus I omega t C down up, where the plus is for the first case of up and the down, and the minus sign is for the second case of down. So you see it just couples up and down. So this is two different differential equations, and we want to solve them. And the way you solve these kinds of things is you want to move into a co-moving frame. So you want to move into the frame where you get rid of this term right here. So imagine, what it looks like is if you don't have the applied field in the XY, right, and the spin is not, it is somewhere, it is at some angle to the B field, it'll precess around with the Larmor frequency, omega naught. So what you do is you just want to move to a co-moving frame where, the spin effectively sits still. And so what do? So you change variables from C up, down. You change to E plus or minus I omega naught T over 2 times some new coefficients, gamma up, down. And that's, in terms of these coefficients, it's like moving to a co-moving frame. So then it's easy. You can just take this, right, and substitute it back into here. And it's easy to see what will happen when you take the derivative with respect to time with this exponential piece. It'll pull down factors of plus or minus omega naught over 2 times I. And it'll cancel this I right here. And that term will cancel this piece right here. So what you get in the end, if you plug this in and you just plug it into all these things and start canceling things, what you get is a set of differential equations for the gamma. And that's, of course, gamma up, down. dt is equal to minus 1/2 omega 1 e to the plus or minus I delta. I'll tell you what delta is in a second. T gamma down, up. Now it's a much easier differential equation because we're only left with these coupling terms. And delta here is the difference between the applied field frequency and the Larmor frequency. And this is often called the detuning. Why is it called the detuning? Because in order to get, the maximal effect here, what you want to do is you want to apply a field that oscillates at the same frequency as your Larmor frequency, as the precession frequency of the spin in just the, the static field. So the detuning tells you how far your applied frequency is away from the Larmor one. So it's called a detuning. And, but you can forget all that for now. We just want to solve this differential equation. Any questions so far? And just solving the time-dependent Schrodinger equation with this Hamiltonian, we're using spin up-down basis to get a differential equation for each of the coefficients here. And then we just changed variables, changed the coefficients by multiplying them by plus or minus I omega naught t over 2 to get rid of this term right here, which is the Larmor precession term. It's the term associated with the diagonal piece, which is, remember, just the energy associated with the field just pointing in the z direction. Okay, so we have this, and let's try to solve it. And of course, we have this parameter that's the detuning. So it's nice to first solve it for delta is equal to 0. That's called it's the resonance condition. So it's at resonance. It means you're applying your oscillating field in the XY direction at just the right frequency to match the Larmor frequency. So it's perfectly matched. And then delta is 0, and the equation becomes much easier to solve, because then what you can do is you can differentiate with respect to, so if this is gone, right? Now there's no time dependence. See, it's nice. Now this is just some constant, right? And what you can do is you can differentiate with respect to t again. And what you get is 2 derivatives on gamma, right? dt squared. And I can sort of multiply both sides by I, and I will get I over 2. There's a minus signs that cancels. There's the omega 1, and then I get d gamma down up, right, dt. And I can substitute in our original equation up here for this, right? And that'll give me another factor of omega 1 and another factor of I. And so what I get is minus omega 1 squared over 4, right? And then it's gamma up, down. The directions flip again. So I just substitute in this equation back. It's kind of a funny trick, but it's a very common thing when you have a system of 2 first-order equations. You can convert it to a single second-order equation by differentiating with respect to time again, and then substituting back in on the right-hand side. So, and now I just get the second-order equation, and that's much easier to solve, right? Because you can just immediately integrate it up. We know what the solutions are for gamma up and down. And yeah, so the solutions are we can write them as follows. So if we define theta as omega 1 times t, then the solutions for gamma up and gamma down can be written as the following matrix multiplication. And I'll show you why it's convenient to write it this way. It's because it reveals the physics that's going on. So what you get is the following solution. I'm just writing it as a matrix multiplication. Of course, it's just the solution to this differential equation times some constant vector, which is a minus ib, where a and b are the initial conditions. So there's second order equation, so that means there's two unknowns that you get, and that's just what a and b are, and they satisfy the following constraint that their magnitudes sum up to 1. That's the normalization. So you see, we just wrote it in this way, but the solutions are just cosines and sines of theta omega 1 t over 2, right? That's what this tells you. You just get complex exponentials, right? The solutions here are e plus, the fundamental solutions are e plus or minus, right? I omega 1 t over 2. So any linear combinations of those work. And good ones to choose are these linear combinations that gives you cosine and sine. So, alternatively, the fundamental solutions are sine theta over 2, where again, theta is omega 1 times t, and cosine theta over 2. And it's just convenient to write them this way, because then your normalization condition can be expressed like this. And why is it convenient? It's because this matrix here, if you look at it, it's a rotation matrix. What it is, in terms of, you can write it in terms of an exponentiated Pauli operator, and it's e to the I theta sigma x over 2 times the a minus ib, which is just the t equals 0 values. It's the initial condition for your gamma coefficients. That's what this solution is. So you see what it's telling you is that what's happening is that this oscillating magnetic field, when it's on resonance, if you think about what that looks like, right? If it's on resonance, imagine this is the spin, if you see my hand here, and it's processing around with the Larmor frequency, omega 1. What you're doing is you're applying a field in XY that rotates along with the Larmor frequency. And if you're in that rotating frame, right, what does that look like? It looks like you're just a stationary spin in an X. And there's a constant X, or there's a constant field applied in the X direction, because the whole thing is just rotating around with the Larmor frequency. So what that looks like from the point of view of the spin in that rotating frame is just as if it's a spin that's at some angle to an applied constant field in the X direction. So what that'll do is it'll make another precession around the X direction in that rotating frame. So you just get another spin precession, except in the orthogonal direction. So that's why it's the rotation matrix here is sigma x and not sigma z, as it was for just the regular Larmor precession. Yeah, so when you're on resonance like that, it looks as if there's just a stationary field along the X direction. The spin precesses around that. It's like a double precession. It's precessing around Z, but in its frame, due to that oscillating field that's resonant, it's also precessing around X. So it's making this complicated kind of motion, but it's easy to see what's going on if you choose the appropriate coordinates, which we did here by transforming from these C coefficients to the gammas. Okay, and on resonance, it's kind of easy to figure out what's going on in terms of we want to know, say, the probability of observing the spin, right, either in up or down. So what are those guys? The probability of observing it in the up direction, well, it's just the inner product between your time-dependent state and the up basis vector. And what is that? Well, we know what the solution is. So these gammas are related to the C's, right, by just a complex phase factor. So this phase factor doesn't do anything in terms of the probabilities. So remember, and this is the C up is the component along the up direction. So this whole thing, that just has to be equal to, that just has to be equal to the magnitude of the gamma up squared. And we know what that is. We can, for instance, assume that we start at psi of t at t equals 0, right? We can start in spin up. We can start, we have to pick our initial condition. So let's just say that at t equals 0, we're in the up direction. What does that mean? That means A is equal to 1 and B is equal to 0 over here. Those are the initial conditions. And so what do you get? Well, if B is equal to 0, then this gamma plus thing is just going to be this term right here. It's just going to be cosine squared omega 1 t divided by 2. And similarly, the up case, the down case is just going to give us the sine squared omega 1 t over 2, because that's this term right here. When we do this, when we multiply it out again, if b is equal to 0 and a is equal to 1, then this whole thing is equal to, right, cosine theta over 2, and then it's I sine theta over 2. Just doing the matrix multiplication there. It's just this guy. Okay, what is that? And so what is this? It means that when we apply this rotating magnetic field on resonance with the Larmor frequency, we cause a flip in the spin, right? It starts with frequency omega 1, which is this Rabi frequency. So if we were to plot, say, the probability as a function of time of being in the up direction, right? What does it look like? Well, it oscillates between 0 and 1. It starts, and so remember, this is something that's initially pointing up, along the B naught direction, the Z direction. This is, initially in this state. And if you apply an oscillating magnetic field in the XY plane, what it does is it starts flipping this spin up and down with a frequency that's given by omega 1. This is the flipping frequency. It was called the Rabi frequency. And remember, that had to do with the magnitude of the applied field in the XY plane. And so, what this looks like is just it oscillates between 1 and 0. So it goes between up and down. It goes between up and down, and these are called Rabi oscillations. And this is kind of the maximal effect, right? This is on resonance. It means this is the most that oscillating field can do. It can actually flip the entire direction of the spin from up to down with this frequency omega 1. So what we will do next time, it's a good place to stop, is we're going to ask what happens if we're not on resonance. what happens if delta is not equal to 0 and we apply this oscillating field at a frequency that's different from the Larmor one? What if we're not on resonance? And then if you can imagine it, then the rotating, what happens in that rotating frame, the oscillating field no longer looks like it's constant. It's no longer rotating with the Larmor frequency, with the spin. It's actually going to start rotating in that rotating frame. And if you start thinking about it, if you average out over that rotation, it's going to have a less of an effect, right? Because it's as if the field is pointing in all directions on average. So we'll see that if you're away from resonance, then you also get Rabi oscillations, but they're smaller. They don't have as big of an effect. And that's what we'll see. And we'll solve that differential equation. You see what will happen is if you can't get rid of this exponential up here, when you take a second derivative with respect to time, you'll just get another term that comes from differentiating with respect to t of this part right here. So we'll see. It just introduces another term to the differential equation. Yeah, but that's it for now. Any questions about that? NMR. Well, it's not really, I didn't really tell you how it's related to NMR, but we sort of covered the N. Well, I'm not going to tell you how the actual apparatus works, but this is the physics of it anyway. So the physics of a spin in a static field with an applied oscillating field in the perpendicular direction. Okay. Yeah, I guess that's it for today. Let me